Hi everyone, welcome to Unit 9 where we're going to talk about AP Calculus topics on the BC exam. In particular, we're going to talk about infinite series. So we've already discussed the concept of a sequence, and a sequence is a list of numbers, and that list can often have a pattern, and we can describe that list of numbers with an equation, with finding what's called the nth term, and that's that equation involving a sub n. Sometimes it's explicit, involving, n, which is what we like. Sometimes it's recursive, which is sometimes easier to come up with, but less useful in the long run. So a finite series takes a partial list of the sequence. So maybe if it's an infinite list of numbers, a finite series will stop at a certain point, and maybe it says we only have 100 terms that we're adding together. You can always find the sum of a finite series. It will always add up to something. What we're going to focus on here, and what your AP exam is going to focus on, is this concept of an infinite series. And we kind of discussed this a little bit in Unit 8 when we talked about improper integrals. And we said when we integrate, remember, we're finding slices and adding up those slices. And we said sometimes those slices will add up to something. And even though we might be integrating that improper integral over what appears to be an infinite space, sometimes those slices added up to something. We said it converged to an area, and then sometimes they didn't converge. Sometimes they diverged and added up to infinity. And we're going to now look at this, and I want you to picture in your mind those integrals and those slicings, because what we're going to do is now we're going to look at lists of numbers and they're related to that slicing. But instead of looking at the slicing and trying to integrate, we're just going to say, here's a pattern of terms. Do they add up to something? And I want you to understand that sometimes they will and sometimes they won't. And we're going to use the same language that we did when we talked about improper integrals. We're going to say either that the series converges and that we can find the sum and it does add up to something, or we're going to say that the series diverges and has no sum and it goes to infinity at some point. So that's the language we're going to continue to use here in this particular lesson and in this unit. So we're going to start out by just kind of considering a couple of these lists of numbers here, and we're going to explore them a little bit using Desmos to help us kind of find some what we call partial sums. And what we do when we have a series, the the rudimentary thing that we would do is we would start taking the terms and we'd kind of add them up and see what they add up to. And so I'm going to kind of bring us over to Desmos, and we're going to take a look at each of these. Now, before I show you what those Desmos summation equations look like with our series, let's first real quick talk about where I'm going to get some of these equations from. So keep in mind that we have to be able to kind of write these out as some sort of like a rule for each term, right? So let's talk a little bit about some notation here. So if I want to figure out a rule for a series, the first thing I'll do is I'll kind of write down some values of n. So n is 1, 2. I'll just number the terms. And here, check it out. This series, an, is just n. So if you want the 100th term, it's just 100. It's literally that. It's just the list of numbers added together. So when I add this together, my summation notation ends up looking like this. N equals 1 to infinity of n. So this would be what this series would look like in that summation notation. So when I get down to this next one, I'm always going to start with, 1, 2, 3, 4, 5. And I'm going to figure out, okay, what's going on here? How can I figure out what this series is? And it really does look like it's powers of 2. It's 2 to some nth power. So when I write this out, I'm going to consider this as being an equals, well, it's 1/2 to some power of n. So look at it. 1/4, the way you get 1/4 is you take 1/2 and you square it. 1/8 comes from 1/2 cubed. So you just have to get good at looking at these patterns, not memorizing them, but just kind of looking for patterns. Sometimes it'll pop right out at you, and sometimes you'll have to kind of stare at it and come back at it with some fresh eyes. It's not something that can be taught. It's just something you get better and better at the more you practice. So there are tricks to look for, and powers like this is one of the tricks. Is it some number raised to a power? So this would kind of look like this. You'd have 1/2 to the nth power, n equals 1 to infinity. Now this is a geometric sequence, or a geometric series. The way that I know it's geometric, remember, the general form is this, but if you start it at 0, then, you know, here n is 1. So you just have to kind of make sure, okay, if I put 1 in, am I getting the same thing? Sometimes if you wanted to make it n minus 1, how would we adjust? Well, we'd have to make n 0. Or I guess, no, it wouldn't be, hold on one sec. Yeah. If you wanted to make it n minus 1, oh, we'd have to start at 2. You'd have to kind of play around with n and make sure you get that right power. The first term is what defines what's happening. You could also pull out a 1/2 and say, oh, it's 1/2, and now it's 1/2 times, you know, n minus 1. And then you could also do it that way. There's lots of things that you could do to kind of make it look more like that series or that sequence rule that we learned. You'll just have to play around with it. But the best way to make sure that you're doing it right is when you plug that first value of n in. If n is 2, 2 minus 1 is 1. 1/2 to the 1 power matches with that first term. So as you're writing out these nth terms and finding these patterns, this is kind of the thinking that we want to do. So then when I jump down to this next one, this would be where n is 1, 2, 3. Oh, hopefully you see the pattern. This one would be the sum of 1 over n, and we would let n start out as 1. Down here, we have an alternating. It's the same series, but this time, I'm going to put a little alternator in there. And when I do my alternator, I need to think about this. If I just make it n, when I put 1 in, I'm going to have negative 1 to the 1 power. That means that my first term would be negative. So when I go over here and I see that this is positive, then I know maybe I need to make an adjustment. So I'm going to change that to a +1. So now it shifts it over so that now these are the positive values, and then when I get to 2, that's going to be an odd power. So you're going to have to play around with it and make sure that everything lines up. The whole point is when you put the values in for n, does it produce that list of numbers? So always go back and double check it and make sure that your thinking is right. And then this last one here, it sure looks like it's 3 times 1 over 10. 3 times 1 over 100. I'm going to think about it like that. And this looks like a geometric series, and I'm multiplying by 1/10 each time. So let's check it out. If I do, let's see, we'll say 3, and then we'll say 1/10 to the n power. And if I let n equal 1, let's make sure it works. When n is 1, I have 3 times 1/10. When n is 2, I have 3 times 1 over 100. So it works out. So I can mess around with it. Remember, a geometric series doesn't have to look like what we talked about here. There are lots of ways that you could manipulate it. The whole point is you're multiplying by 1/10 each time. And when you kind of mess around with this notation, does it produce this list? And if the answer is yes, then you're okay. You could even start this at n equals 0. Sometimes we do that. Sometimes we start at 0 when we count, and that's just kind of crazy to me. Well, if that was the case, then I'd have to adjust the exponent and make it n plus 1. The whole point is when you have the numbers in front of you, do they produce this list? And if they do, then you've done it right. There's no set way to do it correctly other than, hey, if this is an equivalent form and it makes this list, you've done it right. You are okay. Okay, I could even go like this. I could say, oh, I'm going to start n at 5. Well, in that case, it would look like this. 3, and then I'd have to do like n minus 4 to make it give that first one. So there's lots of ways we can manipulate the series and the notation with the n to make it produce that list of numbers. So now that we've talked about how to produce these lists of numbers, let me show you how Desmos can be a helpful tool in finding the partial sums, so we can kind of start to see, do they add up to things? So let's take a look. All right, so here we are in Desmos, and I've plugged in those little functions that we kind of came up with. You can get to Desmos summation notation kind of just down here with the keyboard. If you go to functions and go to miscellaneous, it's right there. And then if you put any value in k up here at top, remember infinity is just kind of this concept. So if you put a k up there, you can add a slider and check it out. If I slide k along, k is 1 now. So if I increase k to like 3, check it out, the sums change. So this means I'm taking the first 3 terms and adding them together. So let's take a look at our sums here. So they're kind of starting to turn into things. So let's take note. So 0.333, 0.833333, 1.8333, okay, 0.875, 6. I think we can already tell that this first one's probably not going to do anything special. Check it out. When I go all the way out to like 100, I'm at 406. And actually, let me just change a setting here. We're going to go real slow and just kind of like see what happens. So here we are. You can kind of see what's happening to the sums. So this sum here is turning to 1. This sum is just exploding. This sum seems to be continuing to increase. We can't tell if it's getting anywhere. But this sum here in number 5, oh, it just started over. So check it out. Watch number 5. Number 5 seems to be approaching something. Kind of goes back and forth, doesn't it, between 0.6 and 0.7. Whereas this one up here that wasn't alternating kind of keeps going. Number 6 converges to 0.3 repeating. Check it out. Oh, here it goes. It started over again. So this will go all the way up to the first 100 terms. So we can kind of see the behavior is such that some of these, like this one here, this n, in slot number 2, and then the one here in slot number 4, they seem to be just kind of getting bigger and bigger and bigger. And if I increased k to something even bigger, it would just keep on going to infinity. But sometimes, like we have this geometric series, which is this 1/2 to the n power, or 1/2 to the n, depending how you write it. They're both the same thing. They converge. So like this is converging to 1. Okay? So check that out. That's pretty cool. And then down here we've got this one, it converged to 0.3 repeating. And then this one that's alternating just bounces back and forth, but it does appear to be converging to something. I'm not sure what though. But it is converging. So yeah, you can kind of see this behavior, and what a great tool Desmos is for kind of showing this. And again, you can do these creations too just by going to desmos.com and graphing and just kind of typing some things in, and just hit play, and you can kind of tool around with the little settings. You can make k go as high as you want. So if we wanted k to go to 1,000, I have no idea what's going to happen here. But as k goes up to 1,000, we can kind of see what's happening here. Look at this 1/n. It just keeps going. It's slowly, but it's just going and going and going. Check it out. Number 2 we're going to run out of memory. But look, slot number 5 here, it continues to just kind of bounce around. Look, it appears to be converging. So there you go. That's that. So let's talk a little bit more about these series. As I mentioned before, we're going to use a lot of the same vocabulary here with series as we did with integrals. A couple little notation things to kind of tidy up here and talk about. Remember, the nth term a sub n is the rule for the series. So it's the rule that produces the list of numbers that we add together. The sigma, that little e that's shown here, this just means add them up. That's a summation notation. So an just produces the list. The e says add up the list. So we have a sequence that we're now adding up, and now we're calling it a series. So an infinite series will have infinity for k up there at the top. In general, that's what we're going to be dealing with here. Now, the partial sums are what we were doing with Desmos. And so sometimes on your assignment, it asks you to start by finding the partial sums. And that just means start by adding on a consecutive term. And if you want to use Desmos to kind of see that, that's a great way to get into it. But we're going to be abandoning that. That's pretty rudimentary. And we're going to be looking for some tests that kind of make it so that we don't have to find those partial sums. And again, if we add up to something, we say it converges. If it doesn't converge, then we say it diverges if it adds up to infinity. So the big idea is we want to know some rules to figure these out, so we don't have to use Desmos, so we don't have to use our calculator, so we have to like add things together. So the first thing we're going to look at are just a couple of tests to tell us if something will converge or diverge. And the most simple test and the easiest one to apply, and you'll apply this every single time no matter what, is something called the nth term test. Now we talked about this with a sequence, and we said the nth term, the limit of the sequence, is what we converge to. And so the idea here is that if the terms are turning into something, we'll be able to tell what we're going to add up to, whether we're going to add up to something or not. And the easiest thing to do is to say, well, the terms have to be going to 0. if the terms are turning into something else, so remember, this is what we did in chapter 8. If the limit, and we used k here, usually we use n, if the limit is approaching 0, well, we aren't guaranteed that it converged, but if the series is converging, then we know that these terms are turning into 0. It's a one-way street. And if the limit does approach 0, that's not good enough to say that it's going to converge, because we know, we saw this series over here. These terms are turning into 0, but it was not adding up to something. This diverged. So just because my series goes to 0 does not guarantee that my series will converge to something. What it means is that if it doesn't go to 0, then you know for sure 100% that it diverges. So this is kind of like, let's just make sure that we're not going to diverge, right? That's kind of the goal of this test. So basically it says this: if the terms aren't getting smaller and smaller and approaching 0, then there's no way you're going to converge. 100% you will not converge. So this right here is kind of the key and the heart. This is what you need to lock in on. This is a divergence test. It's not a convergence test. It's a divergence test. So think of it this way. If your terms are turning into something other than 0, if the terms are turning into 2, then all the way down the line as you approach infinity, you're going to end up with 2 plus 2 plus 2 plus 2 plus 2. And it's going to add up to an infinite quantity. But if your terms are approaching 0, then there's a chance that they might converge. But 100% you know for sure that if the limit of the nth term, if the terms are not turning into 0, then it will diverge. So really, if you're like not into mathy equations and you're just more like a conceptual person, the thing you're going to write down is if the terms are not turning into 0, we would say approaching 0. You are guaranteed to diverge. But if they are turning into 0, then we have to do something else. So the nth term test is always really nice because you can kind of almost always look at it and be like, that's not approaching 0. Diverges. Or, that is approaching 0. Now I need to do this other thing. We're going to learn these other things as time goes on. So the second test that we need to do is the most basic test, and that's a geometric series. And we've talked a little bit about geometric series when we discussed sequences, and I introduced the concept of a series. And what you need to understand is that in a geometric sequence, all we're doing is adding up these terms and calling it a series. So geometric series, it's the same rules from term to term. You're still multiplying by something. And we still kind of write it like this. You can all, you know, it's also kind of, it's just weird. You're not locked into these exponents. Exponents may appear different. The whole goal is, so like for example, when I say differently, you might look like this, 1/2 to the n. You might also look like this, 1/2 to the n. So there's lots of ways that you could look and be a geometric series. The key is when you write out the terms, are you multiplying by something? If a series is geometric, then we can identify R and A from our equation, and we'll converge to this sum. So what I need you to understand is that A is what you get when you plug in the first value of n. R is what is raised to the power. R is the multiplier. So here, when we're talking about this 1/2 to the n, okay, you can rewrite 1/2 to the n as 1/2 to the nth power. So here, R is going to be 1/2. A is going to be, whenever I plug in that first n value, it's going to be 1 over 2 to the 1. A is 1/2. So you have to kind of work for it a little bit. It's not going to always be obvious. You can't just pull things out. It's just not always going to be that first value. So when we find the sum, and let's continue on with this example, the sum will look like this. First things first, whatever r is, it has to be less than 1. So we say that the absolute value of r has to be less than 1. R could be a negative value. So as long as r is between 1 and -1, as you raise it to the power, what's going to happen is your nth term test is going to approach, the nth term will approach 0. So that's number 1. If r is outside of that range, if it's too big, your nth term will approach not 0. It'll just get bigger and bigger. So the idea is that nth term test you only pass the nth term test to move on to the next test if r is less than 1 or greater than -1. So we have that, r is 1/2, so it works. So here, my sum, this series, this 1/2 series, would converge to this. I'd have 1/2 in the numerator, and then 1 minus 1/2. So that gives me 1/2 over 1/2. So this series would add up to 1. How cool is that? We have this great little formula here. So let's take a look at a couple of series and kind of like apply what we know. So first things first. Nth term test is always what we want to use. So on the nth term test, is this limit going to approach 0? Well, I'm taking 1/2 and raising it to a power that's bigger and bigger and bigger. So as I raise 1/2 to a bigger and bigger power, because the 1/2 is less than 1, something smaller than 1 raised to a bigger and bigger power is just going to get smaller. So you're going to be multiplying it by smaller and smaller quantity. It passes the nth term test, which means I need to do something else to prove that it converges. So now I'm going to check and see, is it geometric? And in a geometric sequence, you're going to have something to a power of n. So geometric, something to a power of n. That's always going to be, or it's going to be something raised to some power of n, or it can be 1 over something to the nth power. That you know is a geometric power. Or you could even have a number up here to the nth power because you can pull that number out. The whole idea is that you have something to the nth power floating around. You can make it appear to be a geometric sequence by manipulating things. So here, this is geometric, so I'm going to identify r. r is 1/2. A is what you get when you plug in the first value of n. So 3 times 1/2 to the 1 minus 1, that's going to be 3. So here it did happen to be that value in the front. So because r is less than 1, I'm going to go ahead and use my formula. It is a over 1 minus r, so 3 over 1 minus 1/2. It's going to be 3 over 1/2, and when I flip the 1/2, I get 6. So this converges to 6. It is a geometric series that converges to 6. So let's try this next one. So I have this power -3/5. This is obviously geometric. If you notice that it's geometric, you can just jump to that. So geometric, here r is -3/5. That's between 1 and -1, so it's going to converge, so I'm good. So I need to find what a is. A is whatever I get when I plug in that first value. Ooh, I should start this at 1. I should change that. This is a bad example. 1 minus 1, we'll let a be 1. I don't want k to be 0 because I don't want a -1 power. That just doesn't work for me. It could work. We're going to fix it though. We're just going to let it be 1. So here we go. My sum is a over 1 minus r. So 1 over 1 minus -3/5. Turns into plus a plus. You get 1 over 5/5 plus 3/5. That's 8/5. When I flip it, I get 5/8. Yep. There you go. That's what we converge to, 5/8. If we were to add it up, if we go to Desmos, you could check it out, it would add up to this 5/8, which is like 0.625. So let's keep going. Let's find this next one here. So we've got pi over 2, pi squared over 4. Ooh, this one's not in summation notation. Let's see if we can get it there. What am I multiplying each time? Well, on the top, I'm multiplying by pi. On the bottom, I seem to be multiplying by pi over 2. That's my r. Now let's think about this. There's nothing else I can do if r is too big. So r has to be between 1 and negative 1. Well, pi is like 3.14. Divided by 2. You guys, that's bigger than 1. This diverges. And if you wanted to test it, you would kind of plug it in like this. You'd say, well, it's pi over 2 to the nth power n equals 1 to infinity. That's what you'd plug in, and you could find your partial sums. This is going to add up to an infinite quantity. Last but not least, let's take a look at this one. Oh, x to the n. Oh, this appears to be geometric, where r equals x. Oh, it's a value. It's a variable. Remember, x can be any number. So let's think about this. If this is my infinite series and it's geometric and I want to know, does it converge? Well, if r is x, a would be what I get when I plug that first value in. A is also x. Let's think about this. What does this converge to? Well, my sum says it's a over 1 minus r. Well, assuming that it converges, it would converge to something like this, x over 1 minus x. Interesting. So I have this series that looks like a polynomial, but it also kind of looks like this function. So whatever x is, this will converge to this value. So let's think about this. In order to converge, the absolute value of r has to be less than 1. Well, if r is x, then the absolute value of x has to be less than 1. And what this means is that x has to be between 1 and negative 1. In the same way, r has to be between 1 and negative 1 to converge. So here's the cool part. If I pick any value for x, and I want to know what it converges to, so suppose I want to let x equal 1/3. If x is 1/3, as long as it's between 1 and negative 1, this series will converge to this function. If I let f of x equal x over 1 minus x, f of 1/3 is what this series adds up to. So if I plug in 1/3, I get 1/3 over 2/3. I get 1/2 when I flip that 3/2. So how cool is that? If x is 1/3, this series adds up to 1/2. I've just now created a function where I can have a variable in my series and I can pick any value. So now I've just opened up the gates and I've said, if I have a series here and it looks like this, it models this, I can pick any value for x and it will always converge to this sum, this x over 1 minus x for this series. And this is kind of what we're going to get into. And we're going to see that we have these series and we can use these series to kind of represent functions, and we're going to learn how to kind of see the relationship between them. But the idea is if I have a series, it converges to this function and I can pick any value of x I want and plug it in and it will always work. So that's kind of where we're moving into. That's going to be kind of our next adventure here. But for now, your goal is to identify whether series converge using two different tests. The first thing you're going to do is you're going to do this nth term test, remembering that the nth term test simply says, does it diverge? If it doesn't diverge, then you need to go on to something new. And the only other thing that we have at our disposal right now is a geometric series. So you're going to look and see, can I create a geometric series? Can I tell what r is? And if r is between 1 and negative 1, then I know that it will converge to something. But if r is too big or it's too outside of that little range beyond 1 and negative 1, then it's not going to converge and you can't do anything. You say it diverges and you're done, and because it's going to add up to infinity. But the whole point is it geometric and what does it converge to if it converges? The more you practice this, the better you will become at identifying these series and being able to tell the convergence and being able to use the geometric series formula, which, by the way, is this formula here. Make sure that it is in your notes. We are going to be using this a lot. That is what a geometric series will converge to, provided that r is between 1 and negative 1. So make sure you have that down. The more you practice, the better you're going to become at identifying these. Keep practicing, keep going. You can do this. You got this.